Welcome to this gentle exploration of one of the universe's most enigmatic theoretical constructs, the white hole. Tonight, we drift into a realm where mathematics meets mystery, where the familiar darkness of black holes finds its luminous counterpart in something far stranger and more elusive. Picture, if you will, the universe as a vast cosmic dance floor where matter and energy perform an eternal ballet, choreographed by the fundamental forces of nature. In this dance, we have long known about the cosmic performers that consume everything around them: black holes, those gravitational giants that devour light itself and from which nothing can escape. But what if this cosmic choreography demanded a partner? What if, for every cosmic consumer, there existed a cosmic creator? This is where white holes enter our story, emerging not from observation or discovery, but from the elegant symmetries hidden within Einstein's equations. They represent something both beautiful and unsettling: the mathematical mirror image of black holes, regions of space-time that violate our everyday understanding of causality and flow. While black holes are defined by their event horizons, boundaries beyond which nothing can escape, white holes possess what we might call anti-horizons, boundaries through which nothing can enter. They are not cosmic vacuum cleaners, but cosmic fountains, theoretical regions of space-time that spew matter and energy outward with relentless, unstoppable force. Where black holes represent the ultimate endpoint of gravitational collapse, white holes embody the opposite: explosive expansion and eternal rejection of everything that approaches them. The mathematical elegance of this symmetry is breathtaking. In the equations that govern our universe, for every solution that describes matter falling inexorably toward a gravitational singularity, there exists an equally valid solution describing matter emerging eternally from that same singularity. It's as if nature's fundamental laws were written as a poem, where every verse has its perfect, inverted counterpart. Yet this raises profound questions that have puzzled physicists for decades. If the mathematics of relativity predicts white holes with the same confidence it predicts black holes, why do we observe one but not the other? Why does our universe seem to favor cosmic consumers over cosmic creators? The answer to this mystery leads us into some of the deepest questions about the nature of time, causality, and the fundamental structure of reality itself. As we embark on this contemplative journey through the theoretical landscape of white holes, we find ourselves confronting not just exotic physics, but fundamental questions about the very nature of existence. In a universe where black holes represent endings, the final gravitational collapse of massive stars, white holes represent something even more mysterious: spontaneous beginnings, creation without cause, birth from the void itself. In the quiet depths of 1915, Albert Einstein completed what many consider the most beautiful theory in physics: general relativity. Like a masterful composer crafting a symphony, Einstein had written equations that described the fundamental relationship between matter, energy, space, and time. Yet, within this mathematical symphony lay movements that even Einstein himself didn't fully appreciate: theoretical possibilities so strange that they would take decades to fully comprehend. The Einstein field equations, those 10 elegant expressions that capture the curvature of spacetime itself possess a property that mathematicians call time reversal symmetry. This means that for every solution describing how matter behaves moving forward in time, there exists an equally valid solution describing the same physics running backward in time. It's as if Einstein had unknowingly composed music that could be played both forwards and backwards, each direction revealing different but equally valid melodies. When Karl Schwarzschild solved Einstein's equations for a spherically symmetric mass in 1916, he discovered what we now call the Schwarzschild metric, the mathematical description of spacetime around a black hole. But embedded within this solution, like a hidden theme in a complex musical score, was something else entirely. The complete mathematical description of a white hole, the same equations that predicted regions of spacetime from which nothing could escape also predicted regions from which nothing could enter. This mathematical duality emerges from the fundamental nature of time in relativity theory. Unlike our everyday experience, where time flows inexorably from past to future, Einstein's equations treat time as simply another dimension of spacetime, one that can be traversed in either direction mathematically. When we follow the geometry of spacetime around a black hole forward in time, we see matter falling inward past the event horizon, disappearing from our observable universe. But when we trace the same geometry backward in time, we witness the inverse process. Matter emerging from the singularity, crossing the horizon in the opposite direction, and exploding outward into space. The mathematical beauty of this symmetry is both elegant and unsettling. It suggests that our universe, at its most fundamental level, makes no distinction between creation and destruction, between beginning and ending. The same curvatures of spacetime that create cosmic graveyards also create, in principle, cosmic nurseries, where matter and energy burst forth with violent creativity. Yet Einstein himself was deeply uncomfortable with some of the implications of his own equations. When other solutions emerged, like those describing expanding universes or closed time-like curves, he often dismissed them as mathematical curiosities rather than physical realities. He famously remarked that God does not play dice with the universe, revealing his preference for a cosmos governed by predictable, deterministic laws rather than quantum uncertainties or temporal paradoxes. But mathematics, it seems, has its own logic that transcends human preferences. The equations that successfully predicted the bending of light around the sun, the precession of Mercury's orbit, and the expansion of the universe itself also insist on the theoretical existence of white holes. They emerge not as afterthoughts or mathematical accidents, but as fundamental consequences of the very nature of spacetime. As we drift deeper into this mathematical landscape, we begin to appreciate that Einstein's equations might be telling us something profound about the nature of reality itself. Perhaps our universe is far stranger and more symmetrical than our everyday experience suggests. Perhaps for every cosmic ending, there exists a cosmic beginning. Perhaps destruction and creation are simply different movements in the same cosmic symphony, each as fundamental and necessary as the other. There is something almost musical about the way revolutionary ideas in physics emerge from the interplay between mathematical formalism and physical intuition. The concept of white holes exemplifies this process perfectly. arising not from experimental discovery or observational astronomy, but from the patient mathematical excavation of theoretical physicists who dared to take Einstein's equations to their logical extremes. In 1958, David Finkelstein, a theoretical physicist at Stevens Institute of Technology, was studying the mathematical structure of black hole solutions when he made a remarkable discovery. By carefully analyzing the coordinate systems used to describe space-time geometry, he realized that the standard Schwarzschild solution was incomplete. What others had interpreted as mathematical pathologies, points where the equations seemed to break down, were actually artifacts of the coordinate system itself, like trying to describe the entire Earth using only latitude and longitude lines that converge at the poles. Finkelstein introduced what are now called Finkelstein coordinates, which revealed the complete structure of the Schwarzschild geometry. This mathematical renovation uncovered something extraordinary. The solution naturally divided into 4 distinct regions of space-time. 2 of these regions described what we now recognize as black holes and their exteriors, but the other 2 regions described something that had never been seriously considered: white holes and their relationship to the surrounding universe. Meanwhile, across the Atlantic, other mathematical explorers were making similar discoveries through different approaches. In 1960, Martin Kruskal and George Sikaris independently developed their own coordinate system, the Kruskal-Sikaris coordinates, which revealed the same 4-region structure with even greater mathematical clarity. Their work showed that white holes weren't mathematical accidents or coordinate artifacts, but fundamental features of the geometry of space-time itself. These early pioneers faced a peculiar challenge. They had discovered something that was mathematically inevitable, but physically bizarre. White holes, according to their calculations, would be regions of space-time where matter and energy spontaneously emerged from a singularity, crossed an anti-horizon, and exploded outward into the universe. Unlike black holes, which could form through the gravitational collapse of massive stars, white holes seem to have no plausible formation mechanism. They appeared to exist in the equations without any clear way for nature to create them. The mathematical description was precise and unambiguous. A white hole would possess a singularity at its center, just like a black hole, but this singularity would act as a source rather than a sink. Matter and energy would emerge from this central point, accelerate outward under their own gravitational repulsion, and cross the white hole's boundary, the anti-horizon, beyond which they could never return. The geometry of space-time around a white hole would be identical to that around a black hole, but with the flow of time effectively reversed. Roger Penrose, whose work in the 1960s revolutionized our understanding of space-time geometry, contributed crucial insights into the global structure of these solutions. His conformal diagrams, elegant geometric representations of entire space-time geometries, compressed into finite drawings, revealed how black holes and white holes could be connected through regions called Einstein-Rosen bridges or wormholes. These diagrams suggested that every black hole might be mathematically connected to a corresponding white hole, with the two forming a single, extended object in space-time. Yet even as the mathematical framework became increasingly sophisticated and elegant, The physical interpretation remained deeply puzzling. These early theorists had uncovered what appeared to be cosmic geysers, regions where the universe would spontaneously create matter and energy without any apparent cause or mechanism. The implications were staggering. If white holes could exist, they would represent violations of everything we thought we understood about causality, conservation, and the arrow of time. As we contemplate these early mathematical discoveries, we find ourselves confronting one of the most beautiful and troubling aspects of theoretical physics. Sometimes, the equations know things that we don't yet understand. The mathematics had spoken with crystal clarity about the existence of white holes, but nature remained stubbornly silent about where or whether such objects might actually exist in our universe. In the gentle quietude of theoretical contemplation, few concepts challenge our intuitive understanding of reality as profoundly as the temporal nature of white holes. To truly appreciate these enigmatic objects, we must first release our grip on the comfortable assumption that time flows uniformly forward, carrying cause before effect in an orderly procession from past to future. White holes invite us into a realm where this fundamental ordering of reality becomes negotiable, where the arrow of time itself might point in unexpected directions. Picture, if you will, watching a film of a black hole formation played in reverse. We would see matter and radiation streaming outward from a central point, accelerating away under some invisible force, until eventually the entire structure dissolves into the surrounding space. This reversed film captures something essential about white holes. They are not simply the spatial inverse of black holes, but their temporal inverse, regions where the normal flow of causality appears to run backward. The mathematical description of this temporal reversal is both elegant and unsettling. In the geometry of space-time around a white hole, we find that all time-like paths, the possible trajectories that matter and energy can follow, point outward from the central singularity. This means that anything emerging from a white hole's center is not falling under gravitational attraction, but rather being expelled by what we might think of as gravitational repulsion, the same force that would pull matter inexorably inward toward a black hole's singularity instead pushes matter irreversibly outward from a white hole's core. This creates what physicists call a past horizon, a boundary in space-time beyond which events cannot influence the white hole's interior, while a black hole's event horizon prevents information from escaping to the outside universe. A white hole's past horizon prevents information from entering from the outside universe. It's as if the white hole exists in a state of temporal isolation, disconnected from the causal flow of the surrounding cosmos. The implications of this temporal reversal extend far beyond mere mathematical curiosity. If white holes could exist, they would represent regions where the fundamental principle of causality, the idea that causes precede effects, breaks down in a spectacular way. Matter and energy would emerge from the white hole's singularity not because something caused them to be created, but simply because the geometry of space-time demands their existence. They would represent spontaneous creation without cause, effect without antecedent, a kind of cosmic magic that violates our deepest intuitions about how reality should operate. Yet this apparent violation of causality emerges naturally from the most successful theory of gravity and spacetime that physics has ever produced, Einstein's general relativity, which has passed every experimental test with remarkable precision, inevitably predicts the existence of these temporally reversed regions. The same equations that accurately describe the orbit of Mercury, the bending of light around the sun, and the detection of gravitational waves also insist that spacetime can be organized in ways that challenge our understanding of time itself. The temporal nature of white holes also raises profound questions about the relationship between physics and philosophy. If the fundamental laws of nature permit regions where time effectively flows backward, what does this tell us about the nature of time itself? Is the forward flow of time that we experience in our daily lives merely a statistical accident, an emergent property of complex systems, rather than a fundamental feature of reality? Or do white holes represent a kind of physics that, while mathematically consistent, is somehow forbidden by deeper principles that we don't yet understand? As we drift through these contemplations of temporal reversal and causal violation, we find ourselves confronting mysteries that extend far beyond the specific physics of white holes. These objects serve as windows into fundamental questions about the nature of time, causality, and existence itself. They suggest that our universe might be far stranger and more temporally complex than our everyday experience would lead us to believe. As we drift deeper into this mystery, the time has come to explore the elegant mathematical architecture that governs these theoretical cosmic fountains. There is something profoundly beautiful about how the most abstract mathematical concepts can describe the fundamental structure of reality itself, and nowhere is this more apparent than in the equations that define white hole space-time geometry. The mathematical heart of a white hole lies in what physicists call the maximally extended Schwarzschild solution, a complete description of space-time geometry that encompasses both black holes and white holes as different regions of the same underlying mathematical structure. This solution emerges from Einstein's field equations like a flower blooming in the garden of abstract mathematics, revealing symmetries and connections that our everyday experience could never have prepared us to imagine. At its core, the white hole geometry is described by the same metric tensor that describes black holes, the Schwarzschild metric, but interpreted in a fundamentally different way. The metric d super asers 1 2 gm rc2 dt2 plus 1 2 gm rc2 1 dr2 plus r2 df2 plus r2 sin df2 captures the curvature of spacetime around any spherically symmetric massive object. Yet, within this single mathematical expression lie multiple universes of possibility, multiple regions, where space and time behave in radically different ways. The crucial insight comes from understanding how coordinates behave near what mathematicians call the Schwarzschild radius, the boundary, at Arsadler cars 2 gm c2, where the metric coefficients appear to diverge. Early investigators mistook this mathematical behavior for a physical singularity, not realizing that they were encountering a coordinate artifact, like trying to describe the smooth surface of Earth using a map projection that becomes distorted at the poles. When we extend the coordinates properly, using Kruskal-Shakarian coordinates, A magnificent four-region structure emerges from the mathematics. Region I represents the exterior space-time that we observe around black holes, where space flows inward and time progresses normally. Region 2 describes the black hole interior, where space and time exchange roles and everything falls inexorably toward the central singularity. But the mathematics doesn't stop there. Region 3 emerges as the white hole interior, where the same exchange of space and time coordinates creates the opposite effect. Everything emerges inexorably from the central singularity, expelled outward by the fundamental geometry of spacetime itself. Region 4 represents the exterior spacetime around the white hole, a mirror image of region I, where space flows outward and time progresses in reverse relative to the black hole regions. The mathematical beauty of this structure lies in its perfect symmetry. Every geodesic path that carries matter inward toward the black hole singularity has a corresponding path that carries matter outward from the white hole singularity. Every light ray that disappears beyond the black hole's event horizon has a counterpart that emerges from beyond the white hole's past horizon. The mathematics treats creation and destruction, emergence and collapse, as equally valid and fundamentally equivalent processes. This symmetry extends to the stress-energy tensor, the mathematical object that describes the distribution of matter and energy in spacetime. While a forming black hole is characterized by matter flowing inward and energy density increasing toward the center, a white hole would be characterized by matter flowing outward and energy density that has always been decreasing away from the center. The mathematical signs flip, but the underlying geometric relationships remain perfectly preserved. Perhaps most remarkably, the mathematics reveals that black holes and white holes are not separate objects but different aspects of the same extended space-time geometry. They are connected by what Einstein and Nathan Rosen first described in 1935, bridges of space-time that link the two regions through a kind of cosmic tunnel. These Einstein-Rosen bridges, or wormholes, exist as mathematical necessities rather than optional features of the geometry. The equations also reveal something profound about the nature of information flow in white hole spacetime. While black holes are characterized by information flowing inward across the event horizon and becoming trapped in the interior, white holes exhibit the opposite behavior. Information flows outward across the past horizon and becomes accessible to the exterior universe. This creates what information theorists call a white hole information paradox. If information emerges spontaneously from white holes without any causal mechanism, where does it come from and how is it determined? The mathematical description of white hole horizons is particularly elegant. The past horizon of a white hole is described by the same null surface geometry as the event horizon of a black hole, but with the light cones tilted in the opposite temporal direction. This creates a boundary that is transparent to outgoing radiation, but completely opaque to incoming matter or energy. A one-way membrane that permits only cosmic creation, never cosmic destruction. Yet this is only the beginning of the mathematical story. The complete description of white hole spacetime requires us to consider not just the classical geometry of general relativity, but also the quantum mechanical properties of fields propagating through this curved spacetime, a consideration that will lead us into even deeper mysteries about the fundamental nature of these cosmic fountains. Meanwhile, across the vast expanse of theoretical physics, a brilliant mind was contemplating the deeper implications of these mathematical revelations. Roger Penrose, whose geometric insights had already revolutionized our understanding of spacetime, began to ask uncomfortable questions about whether nature would actually permit the existence of white holes, questions that would lead to one of the most important and controversial principles in modern theoretical physics. In the quiet depths of the 1960s, Penrose was developing powerful, new mathematical tools for analyzing the global structure of spacetime. His conformal diagrams, elegant geometric representations that compress infinite regions of spacetime into finite, comprehensible pictures, revealed the full connectivity between black holes, white holes, and the bridges that link them. But as these diagrams became more sophisticated, they also revealed something troubling. The mathematical solutions that predicted white holes seemed to require initial conditions that were impossibly special, perhaps even unphysical. Penrose's concerns centered around what he began to call naked singularities, regions where the curvature of spacetime becomes infinite but remains visible to outside observers, while black holes hide their singularities behind event horizons. White holes would necessarily expose their singularities to the outside universe, allowing observers to witness the breakdown of physical laws in real time. This possibility struck Penrose as fundamentally unacceptable. Nature, he reasoned, should not permit such cosmic indecency. This insight led Penrose to formulate what he called the cosmic censorship hypothesis, the idea that the universe has built-in mechanisms to prevent naked singularities from forming or persisting. In its strong form, cosmic censorship suggests that any singularity that forms through physical processes must be clothed by an event horizon, hidden from the causal influence of the outside universe. This would effectively forbid the existence of white holes, which by their very nature possess naked singularities that are causally connected to the exterior spacetime. The cosmic censorship principle emerged not from mathematical proof but from deep physical intuition about how the universe should behave. Penrose argued that if naked singularities could exist, they would create regions where the predictive power of physics would break down completely. Near a naked singularity, the curvature of spacetime would become so extreme that quantum effects would dominate, potentially allowing arbitrary amounts of matter and energy to emerge without any causal justification. This would transform physics from a predictive science into something more akin to cosmic magic. But the relationship between cosmic censorship and white holes proved to be more subtle than initially apparent. While white holes do possess naked singularities in their classical description, these singularities exist in the past rather than the future. They represent not the breakdown of predictability going forward in time, but rather the impossibility of predicting backward in time, a different kind of physical pathology that might be more tolerable from the perspective of causal determinism. Penrose's analysis also revealed deeper connections between white holes and the arrow of time itself. He showed that white holes, if they could exist, would necessarily violate what physicists call the second law of thermodynamics. On a cosmic scale, they would represent regions where entropy spontaneously decreases, where disorder transforms into order without any external influence. This thermodynamic violation seemed to Penrose even more problematic than the existence of naked singularities. The cosmic censorship hypothesis sparked decades of intense debate and research. Some physicists embraced it as a fundamental principle that should guide our understanding of gravitational physics. Others argued that it represented an unjustified restriction on the mathematical solutions of Einstein's equations, a kind of aesthetic preference masquerading as physical law. The debate became particularly intense when computer simulations began to reveal situations where cosmic censorship might be violated under specific circumstances. What emerged from this debate was a deeper appreciation for the relationship between mathematical possibility and physical reality. The fact that Einstein's equations permit white hole solutions doesn't necessarily mean that such objects can exist in our universe. The equations might be telling us about mathematical possibilities that are forbidden by other physical principles. Principles related to thermodynamics, quantum mechanics, or the fundamental nature of time itself. Penrose's work also highlighted the importance of initial conditions in determining the evolution of spacetime. While the Einstein equations are deterministic, given appropriate initial and boundary conditions, they cannot tell us which initial conditions are physically reasonable or achievable. White holes seem to require initial conditions that are so special, so precisely tuned, that they might be effectively impossible to realize in any realistic physical process. As we contemplate these deep questions about cosmic censorship and physical possibility, we find ourselves confronting fundamental tensions between mathematical elegance and physical intuition. The same equations that successfully describe the observed universe also predict phenomena that seem to violate our deepest understanding of causality, thermodynamics, and the arrow of time. In wrestling with these tensions, Penrose helped establish a new kind of physics, one that seeks to understand not just what the equations permit, but what nature actually allows. There is something profoundly unsettling about contemplating the thermodynamic properties of white holes, objects that seem to mock our deepest understanding of energy, entropy, and the fundamental direction of physical processes. As we drift into this realm of thermodynamic paradox, we encounter questions that strike at the very heart of why the universe behaves the way it does, why time seems to flow in only one direction, and why disorder tends to increase rather than decrease. The second law of thermodynamics stands as one of the most universal and inviolable principles in all of the physics. It tells us that entropy, a measure of disorder or randomness, can only increase or remain constant in any isolated system. This law explains why hot coffee cools down, why perfume spreads throughout a room, why engines can never be perfectly efficient, and ultimately, why we age and die. It provides the physical foundation for our psychological experience of time's arrow, distinguishing past from future, not through arbitrary convention, but through fundamental physical necessity. Yet white holes, as described by the mathematical solutions of general relativity, appear to violate this sacred principle in the most spectacular way imaginable. A white hole would represent a region where entropy spontaneously decreases, where organized matter and energy emerge from chaos without any external cause or mechanism. It would be as if we could watch a broken vase spontaneously reassemble itself, or witness smoke flowing backward into a chimney to reconstitute the wood that originally burned. The thermodynamic analysis of white holes reveals paradoxes within paradoxes. Consider the process by which matter and energy emerge from a white hole's singularity. In any normal physical process, the total entropy of the system must either remain constant or increase. But matter emerging from a white hole would necessarily have lower entropy than the random quantum fluctuations of empty space from which it appears to arise. This creates what thermodynamicists call an entropy deficit, a violation of the second law that has no known physical mechanism to resolve it. The situation becomes even more puzzling when we consider the thermal properties of white holes. Stephen Hawking's groundbreaking work in the 1970s showed that black holes possess a temperature proportional to their surface gravity and that they emit thermal radiation through quantum mechanical processes. This Hawking radiation allows black holes to reach thermal equilibrium with their surroundings, satisfying the fundamental requirements of thermodynamic consistency. But what about white holes? If they are truly the temporal inverse of black holes, we might expect them to absorb thermal radiation rather than emit it. They would act as perfect heat sinks, cooling their surroundings to absolute zero while growing in mass and decreasing in temperature. This would create what physicists call a thermodynamic instability, a system that amplifies small perturbations until it either stabilizes in a different configuration or destroys itself through runaway feedback effects. The entropy paradox becomes even more acute when we consider information theory. Modern physics has established that information cannot be created or destroyed, only transformed or redistributed. Black holes challenge this principle by appearing to destroy information when matter falls past their event horizons. But white holes present the opposite problem. They appear to create information from nothing, spontaneously generating complex matter and energy configurations without any input of information from the external universe. This information creation problem extends to the quantum mechanical description of white hole formation and evolution. In quantum mechanics, the total information content of any isolated system must remain constant over time, a principle called unitarity that ensures the consistency of quantum mechanical predictions. But white holes seem to violate unitarity by creating new quantum states without any corresponding destruction of existing states. Some theorists have proposed that these thermodynamic paradoxes might be resolved by considering white holes and black holes as parts of a single extended system. In this view, the entropy that decreases near a white hole might be exactly balanced by entropy that increases near a corresponding black hole, connected through the Einstein-Rosen bridge that links them. The total entropy of the combined system would remain constant or increase, preserving the second law while allowing local violations in specific regions. But this resolution raises its own questions about the nature of thermodynamic equilibrium and the flow of energy through space-time. If white holes and black holes are thermodynamically coupled, how does energy flow between them? What determines the equilibrium temperature of the combined system? How do quantum fluctuations propagate through the connecting wormhole? And what happens to causality when thermal information can apparently flow backward in time? Perhaps the most profound implication of these thermodynamic mysteries is what they suggest about the relationship between time and entropy. Our normal experience of time's arrow is intimately connected to the second law of thermodynamics. We remember the past rather than the future, precisely because entropy was lower in the past. But white holes seem to create regions where this relationship breaks down, where entropy decreases as we move forward in time, potentially creating closed causal loops where effect precedes cause. As we contemplate these thermodynamic puzzles, we find ourselves confronting questions that extend far beyond the specific physics of white holes. These objects serve as thought experiments that probe the deepest foundations of physical law, challenging our understanding of time, causality, information, and the fundamental principles that govern the behavior of matter and energy in our universe. Yet this is only the beginning of our exploration into the viability of white holes. For even if we could somehow resolve the thermodynamic paradoxes, even if cosmic censorship could be circumvented, there remains perhaps the most fundamental question of all. Could white holes actually survive in a realistic universe? Or would they self-destruct the moment they encountered any external perturbation? The stability analysis of white holes reveals one of the most elegant and troubling aspects of their theoretical existence. Unlike black holes, which grow more stable as they absorb matter and energy from their surroundings, white holes appear to be fundamentally unstable objects that would destroy themselves through amplification of even the tiniest disturbances. This instability emerges not from exotic quantum effects or thermodynamic considerations, but from the basic geometry of space-time itself. Consider what happens when a small amount of matter, even a single photon, approaches a white hole from the outside universe. In the space-time geometry around a black hole, this matter would be attracted inward, adding to the black hole's mass and making it slightly larger and more stable. But around a white hole, the situation is dramatically different. Any external matter that approaches the white hole's past horizon would encounter what physicists call a blue shifting effect of infinite magnitude. This blue shifting occurs because of the fundamental geometry of the white hole's spacetime. As matter falls toward the past horizon from the outside, it experiences an ever-increasing gravitational time dilation. From the perspective of the external universe, the matter appears to slow down and freeze just outside the horizon. But from the matter's own perspective, the white hole's interior appears to be receding at ever-increasing speed, causing any radiation from the white hole to be shifted to higher and higher frequencies, blue shifted toward infinite energy. The mathematical description of this process reveals its catastrophic nature. Any finite amount of matter approaching a white hole would, from its own reference frame, observe the white hole's interior radiation blue shifted to infinite frequency and infinite energy density. This creates what relativists call a mass inflation effect, a runaway process where the apparent energy density grows without bound, eventually overwhelming the white hole's own gravitational field and destroying the entire space-time structure. This instability is not merely a theoretical curiosity, but a fundamental feature of white hole geometry that cannot be avoided or engineered away. It emerges from the same mathematical structure that gives white holes their defining characteristics, the very geometry that prevents matter from entering the white hole's interior also ensures that any attempt by external matter to interact with the white hole leads to catastrophic collapse of the entire system. The instability becomes even more pronounced when we consider quantum mechanical effects. The vacuum of empty space is not truly empty, but filled with quantum fluctuations, virtual particle pairs that spontaneously appear and disappear on microscopic timescales. Near a white hole's past horizon, these quantum fluctuations would be subject to the same infinite blue shifting effects as classical matter, creating what physicists call a quantum backreaction that amplifies the instability beyond any possibility of control. Stephen Hawking and other researchers have shown that these quantum effects would cause white holes to develop what are called Cauchy horizons, surfaces in spacetime where the curvature becomes infinite and the laws of physics break down. These Cauchy horizons would form spontaneously as a result of the blue shifting instability, effectively destroying the white hole before it could interact meaningfully with the external universe. The stability analysis also reveals interesting connections to the cosmic censorship hypothesis we encountered earlier. The instabilities that destroy white holes can be understood as nature's way of enforcing cosmic censorship, preventing the formation of naked singularities by making white holes self-destruct before they can influence the causal structure of spacetime. In this view, the instability is not a bug, but a feature, a built-in mechanism that preserves the predictability and consistency of physical law. But perhaps the most profound implication of white hole instability is what it suggests about the relationship between mathematical possibility and physical realizability. The fact that Einstein's equations admit white hole solutions doesn't guarantee that such solutions are stable or achievable through any realistic physical process. The mathematics might be describing theoretical possibilities that are forever forbidden by the dynamic instabilities inherent in their own structure. This raises deep questions about the nature of physical law itself. Are the fundamental equations of physics describing all possible realities, or only those that can achieve stable, long-term existence? Is there a selection principle operating in the universe that favors stability and predictability over mathematical completeness and symmetry? As we drift through these contemplations of stability and instability, we find ourselves appreciating a beautiful irony. White holes might be too perfect, too symmetrical, too mathematically elegant to survive in the messy, complex reality of our actual universe. They represent a kind of theoretical purity that reality itself cannot sustain, mathematical poetry that dissolves the moment it encounters the prose of physical existence. In the gentle embrace of quantum contemplation, we must now venture beyond the classical realm of Einstein's relativity into the strange and beautiful world where quantum mechanics meets gravitational physics. Here, in this liminal space, between the large and the small, between the curved geometry of space-time and the probabilistic dance of particles and fields, white holes reveal new layers of mystery that both complicate and enrich our understanding of these cosmic enigmas. The marriage between quantum mechanics and general relativity has never been an easy one. These two pillars of modern physics speak in fundamentally different languages, one describing the smooth curvature of space-time, the other revealing the discrete, probabilistic nature of matter and energy at the smallest scales. Yet, when we attempt to understand white holes in their full complexity, we cannot avoid this quantum realm, for it is here that some of the most profound questions about their existence find their most intriguing answers. Stephen Hawking's groundbreaking discovery in the 1970s showed us that black holes are not perfectly black but emit a subtle radiation through quantum mechanical processes. This Hawking radiation emerges from the quantum vacuum near the event horizon, where virtual particle pairs are separated by the black hole's gravitational field. One particle falls inward while its partner escapes outward, creating a steady stream of thermal radiation that carries information about the black hole's properties. But what happens when we apply this same quantum analysis to white holes? The situation becomes immediately more complex and philosophically challenging. While black holes emit particles that were created near the event horizon, white holes would seem to require particles to be destroyed near the past horizon, a process that appears to violate fundamental conservation laws and the unitarity of quantum mechanics. The quantum vacuum near a white hole's past horizon presents us with what might be called negative Hawking radiation, a process where the vacuum itself would need to absorb energy and information rather than emit it. This creates a kind of quantum paradox. How can the vacuum, which represents the lowest possible energy state of any quantum field, absorb additional energy without violating the fundamental principles that govern quantum systems? Recent developments in quantum field theory in curved spacetime have revealed even more subtle aspects of this quantum behavior. When quantum fields propagate through the complex geometry of white hole spacetime, they experience what physicists call mode mixing, a phenomenon where different quantum states become entangled in ways that depend on the detailed structure of the spacetime geometry. This quantum entanglement extends across the entire white hole structure, creating correlations between the interior and exterior regions that transcend classical notions of spatial separation. Perhaps most intriguingly, the quantum description of white holes reveals connections to some of the most profound mysteries in modern physics. The information paradox that we will explore more fully in our next contemplation emerges naturally from the quantum description of white holes. If quantum information cannot be created or destroyed, but only transformed, then white holes present us with a fundamental challenge. They appear to create information from nothing, violating one of the most basic principles of quantum mechanics. The quantum uncertainty principle also plays a fascinating role in white hole physics. This principle tells us that we cannot simultaneously know both the exact position and momentum of any quantum system. There is always a fundamental fuzziness to the properties of particles and fields. Near a white hole's past horizon, this quantum fuzziness becomes amplified by the extreme curvature of spacetime, creating what theorists call quantum stress energy fluctuations that can dramatically affect the stability and evolution of the white hole itself. These quantum fluctuations introduce an element of fundamental unpredictability into white hole physics that goes beyond classical instabilities. Even if we could somehow create a perfectly classical white hole, the quantum vacuum around it would be filled with random fluctuations that could trigger the catastrophic instabilities we discussed earlier. In a sense, quantum mechanics provides another layer of protection against the formation of white holes, ensuring that they remain theoretical curiosities rather than observable realities. Yet quantum mechanics also suggests intriguing possibilities for white hole formation through purely quantum processes. Some theorists have proposed that white holes might arise spontaneously from quantum fluctuations in the very early universe, when the energy density was so high that quantum effects dominated over classical gravity. These quantum white holes would be microscopic objects, far smaller than atomic nuclei, but they might leave observable signatures in the cosmic microwave background or other relics of the early universe. The application of quantum mechanics to white holes also reveals beautiful connections to other areas of theoretical physics. The quantum description of white hole horizons shares mathematical structures with the theory of quantum phase transitions, where matter undergoes sudden changes in its fundamental properties. The quantum entanglement between white hole interiors and exteriors resembles the entanglement patterns found in quantum field theories that describe the fundamental particles and forces of nature. As we drift through these quantum contemplations, we find ourselves appreciating how the microscopic world of quantum mechanics and the cosmic scale of gravitational physics are intimately connected. White holes serve as theoretical laboratories where these connections become most apparent, revealing deep symmetries and relationships that extend far beyond the specific physics of these exotic objects. The quantum description of white holes also highlights the provisional nature of our understanding. Just as quantum mechanics revolutionized our understanding of atoms and molecules in the early 20th century, the quantum theory of gravity, still under development, may revolutionize our understanding of black holes, white holes, and the fundamental structure of space-time itself. In this ongoing revolution, white holes remain both guides and mysteries, pointing us toward deeper truths about the quantum nature of reality. There is something deeply poetic about the possibility that white holes might hold the key to understanding the greatest mystery in cosmology, the origin of our universe itself. As we contemplate this connection, we find ourselves drawn into questions that span the entire history of cosmic existence, from the first moment of creation to the ultimate fate of everything we know and love. The Big Bang, that primordial moment when space and time began their cosmic expansion, has long puzzled physicists and philosophers alike. How can something emerge from nothing? What caused the initial expansion? Why did the universe begin with such precisely tuned conditions that galaxies, stars, planets, and ultimately life itself could emerge from the primordial chaos? These questions have driven decades of theoretical research and cosmological observation, yet they remain as mysterious today as when first contemplated. In this context, white holes offer a tantalizing possibility. What if the Big Bang itself was not the beginning of everything, but rather the emergence of our universe from a white hole? This idea, first seriously considered by theoretical physicists in the 1960s and 1970s, suggests that our entire observable universe might be the interior of a white hole, with the Big Bang representing the moment when matter and energy first emerged. From the white hole's central singularity, the mathematical similarities between the Big Bang and a white hole are striking and profound. Both involve the emergence of matter and energy from a singular point in space-time. Both exhibit the same pattern of expansion and cooling as material moves away from the central source. Both seem to require initial conditions that are impossibly special and precisely tuned, and both challenge our understanding of causality by appearing to create something from nothing. When we examine the geometry of spacetime in white hole solutions, we find that the interior region, the space inside the past horizon, naturally exhibits the same kind of expansion that characterizes our observable universe. Matter, emerging from the white hole's singularity, would experience this expansion as a cosmic stretching of space itself, exactly what we observe in the recession of distant galaxies and the cooling of the cosmic microwave background radiation. This white hole cosmology model also offers potential explanations for some of the most puzzling features of our universe. The horizon problem in standard Big Bang cosmology asks why regions of the universe that could never have been in causal contact appear to have the same temperature and properties. But if our universe emerged from a white hole, all regions would have originated from the same singular source, naturally explaining their similar properties. The flatness problem, which questions why the geometry of space appears to be so precisely balanced between expansion and contraction, also finds a natural explanation in white hole cosmology. The interior geometry of a white hole automatically produces the critical density and expansion rate that we observe in our universe without requiring the fine-tuning that seems necessary in standard cosmological models. Perhaps most intriguingly, the white hole model offers a natural explanation for the arrow of time and the low entropy of the early universe. In standard cosmology, we must assume that the universe began in an extremely low entropy state for reasons that remain mysterious. But if the Big Bang was the emergence from a white hole, the low entropy would be a natural consequence of the white hole's geometric properties. Matter emerging from a singular point would necessarily be in a highly organized, low entropy configuration. Some theorists have even proposed that our universe might be connected through its white hole origin to other universes through a network of Einstein-Rosen bridges. In this multiverse scenario, every white hole could give birth to a new universe, while every black hole could serve as a portal connecting different cosmic domains. Our universe would be just one member of an infinite family of connected cosmic bubbles, each emerging from its own white hole and potentially giving birth to new universes through the formation of black holes. The observational implications of white hole cosmology are subtle but potentially detectable. If our universe emerged from a white hole, there might be remnant signatures in the cosmic microwave background, subtle patterns or asymmetries that reflect the geometry of the originating white hole. Some researchers have claimed to detect such patterns, though the evidence remains controversial and subject to alternative interpretations. The quantum aspects of white hole cosmology add another layer of complexity and beauty to these ideas. Quantum fluctuations in the white hole's interior could seed the formation of the first structures in our universe, the tiny density variations that eventually grew into galaxies, stars, and planets. This would provide a natural mechanism for structure formation that emerges directly from the quantum properties of the white hole geometry. Yet the white hole model of cosmic origin also faces significant challenges. The stability problems that plague white holes in general would seem to apply equally to cosmological white holes. How could a white hole persist long enough to give birth to an entire universe? how would it avoid the catastrophic instabilities that we explored earlier? These questions remain open areas of active research. The philosophical implications of white hole cosmology are profound and unsettling. If our universe emerged from a white hole, what existed before that emergence? Was there a parent universe containing the original white hole? How far back does this cosmic ancestry extend? The model seems to push the question of ultimate origins back one level without truly resolving it. Instead of asking why something emerged from nothing, we must ask why white holes exist and what determines their properties. As we contemplate these cosmic connections, we find ourselves appreciating how white holes serve as bridges between the largest and smallest scales of physics, connecting the quantum realm to cosmic evolution, mathematical abstractions to observational astronomy, and scientific inquiry to the deepest philosophical questions about existence itself. Meanwhile, across the vast mathematical landscape of general relativity, we encounter one of the most beautiful and mysterious structures that spacetime geometry can create: the Einstein-Rosen bridges that connect black holes to white holes across the cosmic void. These wormholes, as they came to be known, represent more than mere theoretical curiosities. They embody the profound interconnectedness that lies at the heart of Einstein's geometric vision of the universe. The story of wormholes begins with Einstein himself working alongside his colleague Nathan Rosen in 1935. They were exploring the complete mathematical structure of the Schwarzschild solution when they discovered something unexpected. The geometry naturally extended beyond the black hole's event horizon into regions that seemed to describe entirely different areas of spacetime. What they had found was a kind of cosmic tunnel, a bridge connecting what appeared to be two separate universes through the interior of a black hole white hole system. In the elegant language of differential geometry, these Einstein-Rosen bridges emerge as natural consequences of the maximally extended Schwarzschild solution. The four-region structure that we explored earlier, with its black hole and white hole regions connected through interior domains, creates what topologists call a non-trivial spatial connectivity. Space itself becomes multiply connected, like a cosmic Klein bottle, where distant regions curve back to touch each other through higher dimensional tunnels. The geometry of these wormholes is both beautiful and strange. Imagine, if you will, taking a flat sheet of paper and creating two holes in it, then connecting these holes with a tube that passes through a third dimension. From the perspective of creatures living on the surface of the paper, the two holes would seem completely disconnected, but through the tube, they could travel from one hole to the other, taking a shortcut through the higher dimensional space that surrounds their two-dimensional world. Wormholes create similar shortcuts through the four-dimensional space-time of our universe. Two regions that might be separated by millions of light years through ordinary space could potentially be connected by a wormhole that provides a much shorter path through the curved geometry of space-time. The white hole end of the wormhole would serve as an exit point where matter and energy emerge, while the black hole end would serve as an entrance point where they disappear from our observable universe. But the relationship between wormholes and white holes reveals deeper mysteries about the nature of causality and information flow. In the classical description, matter falling into a black hole would travel through the wormhole and emerge from the corresponding white hole. This creates a kind of cosmic recycling system where matter is neither created nor destroyed, but simply transferred from one region of spacetime to another through the curved geometry of the wormhole itself. The mathematical description of this process is elegant but conceptually challenging. The proper time experienced by matter traveling through the wormhole would be finite. A traveler falling into a black hole would experience a definite, measurable journey through the wormhole interior, but the coordinate time, as measured by outside observers, would behave very differently on the black hole and white hole sides of the system, creating apparent paradoxes about simultaneity and causal ordering. John Wheeler, the physicist who coined the term wormhole, became fascinated by these structures and their implications for the fundamental nature of space and time. He proposed that at the smallest scales, the Planck scale, where quantum effects dominate, space-time might be filled with a quantum foam of tiny wormholes constantly appearing and disappearing. This would give space itself a kind of microscopic structure, like a sponge filled with holes that connect different regions through quantum tunnels. The quantum mechanical description of wormholes reveals even more exotic possibilities. Quantum fields propagating through wormhole geometries exhibit what physicists call non-local correlations. Measurements made near the black hole entrance can instantly affect the quantum state of fields near the white hole exit, regardless of the spatial separation between these regions. This creates a kind of quantum entanglement that spans cosmic distances, potentially allowing for faster-than-light communication or travel under certain circumstances. But these same quantum effects also raise serious questions about the stability and traversability of wormholes. Quantum field theory calculations suggest that most wormhole solutions would be unstable against small perturbations, collapsing or becoming non-traversable before any information could pass through them. The vacuum fluctuations of quantum fields would typically cause the wormhole throat to pinch off, severing the connection between the black hole and white hole regions. Some theoretical physicists have proposed that exotic matter with negative energy density might be required to keep wormholes open and traversable. This exotic matter would violate what physicists call the weak energy condition, a fundamental assumption about the properties of matter and energy that underlies many of our theoretical predictions. The existence of such matter remains highly speculative, though some quantum effects do seem to produce localized regions of negative energy density under specific circumstances. The relationship between wormholes and white holes also illuminates deep questions about the nature of time and causality. If wormholes could remain stable and traversable, they might create closed time-like curves, paths through space-time that loop back to their own past. A particle could potentially travel through a wormhole and arrive at a time and place that precede its own departure, creating the possibility of grandfather paradoxes and other causal anomalies. These temporal aspects of wormhole physics have inspired decades of research into the consistency of general relativity with quantum mechanics. Some physicists argue that nature must have built-in mechanisms, perhaps related to quantum effects or thermodynamic principles, that prevent the formation of closed time-like curves and preserve the causal structure of spacetime. Others suggest that such curves might be permissible, but would be subject to self-consistency conditions that prevent logical paradoxes from arising. As we contemplate these cosmic bridges connecting black holes to white holes across the universe, we find ourselves appreciating how general relativity reveals connections and symmetries that transcend our everyday experience of space and time. Wormholes remind us that the universe may be far more interconnected than it appears, with distant regions linked through the hidden geometry of curved space-time itself. There is something profoundly unsettling about the way white holes challenge our understanding of information and its role in the fundamental structure of reality. As we drift into this final contemplation of quantum paradoxes and informational mysteries, we encounter questions that strike at the very heart of what it means for physical laws to be consistent, predictable, and logically coherent. The information paradox has haunted theoretical physics since Stephen Hawking first calculated that black holes emit thermal radiation in the 1970s. The paradox arises from a fundamental tension between general relativity and quantum mechanics. If black holes evaporate completely through Hawking radiation, what happens to the information that fell into them? Quantum mechanics insists that information cannot be destroyed. It can only be transformed or redistributed. Yet Hawking's original calculations suggested that the thermal radiation carries no information about the matter that formed the black hole. This paradox has driven decades of intense research, leading to revolutionary ideas about the holographic nature of space-time, the emergence of space from quantum entanglement, and the fundamental limits of information storage in gravitational systems. But white holes present us with what might be called the reverse information paradox, a mirror image of the black hole, problem that is equally challenging and perhaps even more philosophically troubling. While black holes appear to destroy information, white holes appear to create it. Matter and energy emerging from a white hole's singularity would necessarily carry information about their quantum states, their spatial distributions, their momentum configurations, and their internal properties. But where does this information come from? In the standard description of white holes, there is no mechanism for determining or controlling what emerges from the white hole interior. The information appears to be created spontaneously, without any causal connection to previous physical processes. This information creation problem becomes even more acute when we consider the quantum mechanical description of white hole formation and evolution. In quantum mechanics, the total amount of information in any isolated system must remain constant, a principle called unitarity that ensures the consistency of quantum predictions. But white holes seem to violate unitarity in the most spectacular way possible, creating new quantum states without any corresponding destruction of existing information. Some theorists have proposed that the information paradoxes of black holes and white holes might be related. That information destroyed by black holes might somehow be recreated by white holes through connections mediated by Einstein-Rosen bridges. In this view, the universe would conserve information globally while allowing local violations in specific regions. Information falling into black holes would travel through wormholes and emerge from corresponding white holes, preserving the total information content of the universe while creating the appearance of information destruction and creation in localized regions. But this resolution raises its own puzzles about the mechanism of information transfer through wormholes. How would quantum information propagate through the highly curved space-time of the wormhole interior? What determines which information emerges from which white hole? How would the quantum entanglement between black hole and white hole regions be maintained across cosmic distances and through the extreme gravitational fields of the wormhole geometry. Recent developments in quantum information theory and holographic principles have suggested even more radical possibilities. Some researchers propose that white holes might emerge naturally from the quantum information processing that occurs in black hole interiors. In this view, the apparent information creation of white holes would actually represent information transformation, existing information being processed and redistributed in ways that create the appearance of spontaneous emergence. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary surface, offers another perspective on white hole information paradoxes. If information is fundamentally encoded on the boundaries of space-time regions rather than in their interiors, then white holes might represent regions where boundary information is being decoded and projected into the interior volume. The information would not be created from nothing, but would represent the decoding of information that already existed in the holographic boundary. These informational aspects of white holes also connect to some of the deepest questions in quantum foundations. The measurement problem in quantum mechanics asks how definite outcomes emerge from quantum superpositions during the process of observation. White holes might serve as natural quantum measurement devices, where superposed quantum states emerging from the singularity undergo spontaneous collapse into definite configurations as they interact with the external universe. The connection between information and entropy adds another layer of complexity to these paradoxes. Information theory tells us that entropy and information are intimately related. High entropy corresponds to low information content, and vice versa. The thermodynamic paradoxes of white holes that we explored earlier are thus directly connected to their informational properties. Regions where entropy spontaneously decreases are also regions where information spontaneously increases, creating violations of both thermodynamic and informational conservation laws. Perhaps the most profound implication of the white hole information paradox is what it suggests about the nature of physical reality itself. If white holes could exist, they would represent regions where the fundamental predictability of physics breaks down, not because the equations become mathematically intractable, but because the information needed to make predictions is created rather than conserved. This would transform physics from a science of mathematical determinism into something more akin to cosmic creativity, where new possibilities emerge spontaneously from the geometry of space-time itself. As we contemplate these informational mysteries, we find ourselves confronting the limits of human understanding and the boundaries of scientific knowledge. White holes serve as theoretical microscopes that reveal the deep tensions between our most successful physical theories, highlighting questions that may require entirely new conceptual frameworks to resolve. In wrestling with these paradoxes, we are not merely exploring exotic theoretical constructs, but probing the fundamental nature of information, causality, and existence itself. There is something profoundly beautiful about the possibility that our universe might not be unique, that somewhere in the vast mathematical landscape of general relativity, white holes could serve as cosmic wombs, birthing entirely new universes through processes that challenge our deepest assumptions about creation, causality, and the nature of existence itself. As we drift into this contemplation of cosmic reproduction, we find ourselves exploring ideas that blur the boundaries between physics and philosophy, between mathematical possibility and ultimate reality. The concept of cosmic reproduction through white holes emerges from some of the most speculative yet mathematically rigorous theories in modern cosmology. Just as biological organisms reproduce by creating new individuals that carry forward their genetic information, perhaps the universe itself possesses mechanisms for reproduction, ways of creating new cosmic domains that inherit the fundamental constants and physical laws of their parent universe. Lee Smolin, a theoretical physicist at the Perimeter Institute, has proposed one of the most intriguing versions of this idea through his theory of cosmological natural selection. In Smolin's vision, every black hole that forms in our universe could potentially give birth to a new universe through its connection to a corresponding white hole. As matter falls into a black hole, it might not simply disappear, but instead travel through the wormhole, connecting the black hole to its white hole partner, emerging as the Big Bang of an entirely new cosmic domain. This process would create what cosmologists call baby universes, cosmic offspring that begin their existence as white hole explosions in dimensions perpendicular to our own spacetime. These baby universes would be causally disconnected from their parent universe once formed, developing their own physical laws, fundamental constants, and evolutionary pathways. Yet they would inherit certain characteristics from their parent, perhaps the basic structure of physical law, the dimensionality of spacetime, or the mechanisms that allow for further cosmic reproduction. The mathematics of this cosmic reproduction process involves concepts from topology and higher dimensional geometry that stretch the boundaries of human visualization. When a black hole reaches a certain critical mass or energy density, the Einstein-Rosen bridge, connecting it to its white hole partner, might undergo what mathematicians call a topological transition. The space-time geometry would restructure itself, allowing the white hole region to separate from the parent universe and begin expanding as an independent cosmic domain. In this scenario, the properties of the baby universe would be determined by the characteristics of the parent black hole. Black holes formed from different types of matter, with different spins and charges, might give birth to universes with slightly different physical constants, alternative particle physics, or modified gravitational laws. Over cosmic timescales, this would lead to a kind of Darwinian evolution of universes, where cosmic domains that are better at producing black holes would have more offspring, gradually populating the multiverse with universes optimized for complexity and structure formation. The implications of this cosmic reproduction model extend far beyond theoretical physics into questions of meaning and purpose in the universe. If our cosmos is just one member of an enormous family of reproducing universes, what does this tell us about our place in the grand scheme of existence? Are we living in a universe that has been naturally selected for its ability to create stars, galaxies, and ultimately the complex chemistry that enables life? Or are we simply witnesses to one random branch in an infinite tree of cosmic possibility? Recent developments in string theory and quantum gravity have added new dimensions to these speculations about cosmic reproduction. Some string theorists propose that the fundamental constants of physics, the strength of gravity, the charge of the electron, the mass of the proton, might not be truly constant across all possible universes. Instead, they might be determined by the specific way that extra dimensions of space are curled up and compactified in each cosmic domain. Baby universes, born from white holes, might inherit slight variations in these compactification patterns, leading to entire families of universes with subtly different physical properties. The energy requirements for cosmic reproduction through white holes are staggering and beautiful to contemplate. Each baby universe would begin with the energy equivalent of all the matter that fell into the parent black hole, but compressed and reorganized according to the quantum mechanical laws that govern white hole emission. This energy would then drive the initial expansion and cooling that characterizes the early stages of cosmic evolution, providing the raw material from which stars, galaxies, and eventually life itself could emerge. But perhaps the most profound aspect of cosmic reproduction through white holes is what it suggests about the nature of time and causality across multiple universes. Each baby universe would begin its existence with its own independent time coordinate, its own causal structure, and its own arrow of time, pointing from its white hole, birth toward its ultimate fate. The parent and child universes would be connected through their shared history, but would evolve along completely independent temporal paths, creating a kind of cosmic family tree that branches through higher dimensional spacetime. Yet this cosmic reproduction model also faces significant theoretical challenges that remind us of the speculative nature of these ideas. The stability problems that plague white holes in general would seem to apply equally to cosmological white holes, giving birth to baby universes. How could such objects persist long enough to complete the universe creation process? What prevents the quantum instabilities and thermodynamic paradoxes from destroying the white hole before it can birth its cosmic offspring? Some theorists have proposed that the extreme conditions present during universe formation might somehow stabilize white holes against these destructive instabilities. The enormous energy densities and exotic matter configurations present during cosmic birth might create feedback effects that prevent the usual catastrophic collapse of white hole spacetime. Alternatively, the universe creation process might be inherently quantum mechanical, occurring through tunneling effects that bypass the classical instabilities entirely. As we contemplate these possibilities of cosmic reproduction, we find ourselves appreciating how white holes serve as bridges between the mathematical abstractions of theoretical physics and the deepest questions about existence, purpose, and our place in the cosmos. Whether or not baby universes actually emerge from white holes, the very possibility reminds us that our universe might be part of something far grander and more complex than we have ever imagined. Meanwhile, across the vast expanse of observational astronomy, scientists have spent decades searching the cosmos for any trace of these theoretical white holes, any signature that might reveal their presence in the actual universe that surrounds us. This search represents one of the most challenging quests in modern astrophysics. How do you find something that theory predicts should be almost impossible to create, maintain, or observe? The observational signature of a white hole would be unlike anything else in the known universe. While black holes reveal themselves through their gravitational effects on surrounding matter through the brilliant accretion disks of material falling inward and through the gravitational waves they emit when they merge. White holes would exhibit the opposite characteristics. They would be cosmic geysers, regions where matter and energy emerge spontaneously from apparently empty space, creating expanding shells of material that carry no obvious causal connection to their source. If white holes existed as persistent objects in our universe, they would most likely appear as point sources of continuous matter and energy emission. Astronomers would observe them as objects that grow brighter over time rather than dimmer, that emit material outward rather than absorbing it inward, and that seem to violate the normal thermodynamic principles that govern stellar evolution and galactic dynamics. They would be cosmic fountains in a universe of cosmic drains. The spectroscopic signature of white hole emission would be particularly distinctive, unlike the thermal radiation from ordinary stars, which follows predictable patterns related to stellar composition and temperature. White hole emission would carry information about the quantum mechanical processes occurring near the white hole's past horizon. This might produce unique spectral features, emission lines at unexpected frequencies, polarization patterns unlike those seen from any known astrophysical source, or temporal variations that reflect the exotic physics of the white hole interior. Yet, despite decades of increasingly sophisticated observational surveys, astronomers have never identified a confirmed white hole candidate. The Hubble Space Telescope, the Chandra X-ray Observatory, the Kepler Planet Hunting Mission, and countless ground-based surveys have cataloged millions of celestial objects, from nearby asteroids to the most distant galaxies visible in the observable universe. None of these observations has revealed the characteristic signatures that would identify an object as a white hole. This observational absence might seem to suggest that white holes simply don't exist in our universe, that they remain mathematical curiosities with no physical reality. But the situation is more subtle and intriguing than this simple interpretation would suggest. The very properties that would make white holes theoretically possible might also make them practically impossible to observe or identify with certainty. Consider the fundamental instability problems that we explored earlier. If white holes are inherently unstable against even microscopic perturbations, they might exist only for incredibly brief moments before destroying themselves through quantum back reaction effects. A white hole might form through some exotic process, emit a brief burst of matter and energy, and then collapse into a more stable configuration before astronomical observations could detect and characterize it. This temporal instability suggests that white hole signatures might appear not as persistent objects, but as transient events, cosmic explosions or outbursts that occur too quickly to be easily distinguished from other high-energy astrophysical phenomena. The universe is filled with transient events, supernovae explosions, gamma-ray bursts, stellar flares, and galactic outflows that create brief, intense sources of matter and energy emission. Could some of these events actually represent the brief existence and rapid collapse of white holes? Some researchers have speculated that certain classes of unexplained astronomical phenomena might actually represent white hole signatures in disguise. Fast radio bursts, brief, intense pulses of radio emission that appear randomly across the sky exhibit some characteristics that could potentially be consistent with white hole behavior. They appear suddenly without obvious progenitor sources, emit enormous amounts of energy in extremely short time periods, and often show no repeat activity, suggesting a one-time destructive event. Similarly, some gamma ray bursts, the most energetic explosions known in the universe, might potentially represent white hole formation and immediate collapse. These events release more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime, and they appear to emerge from regions of space with no obvious pre-existing energy source. While conventional models explain these bursts through stellar collapse or neutron star mergers, the white hole interpretation remains a speculative but intriguing possibility. The search for white hole signatures has also been complicated by the problem of cosmic censorship and observational selection effects. If cosmic censorship mechanisms prevent white holes from forming or persisting in realistic astrophysical environments, then the white holes that do exist might be hidden from view by their own exotic physics. They might exist inside event horizons where we cannot observe them, or in regions of space-time that are causally disconnected from our observable universe. Recent advances in gravitational wave astronomy have opened new possibilities for white hole detection. The LIGO and Virgo detectors, which have revolutionized our understanding of black hole mergers and neutron star collisions, might potentially detect the gravitational signatures of white hole formation or collapse. The spacetime vibrations created by white hole processes would carry unique temporal signatures, gravitational waves that emerge from apparent nothingness rather than from the collision or acceleration of visible matter. The upcoming generation of space-based gravitational wave detectors, including the Laser Interferometer Space Antenna, LISA, will have the sensitivity to detect much subtler gravitational effects over longer time periods. These instruments might reveal the existence of white holes through their indirect gravitational influence on surrounding matter, even if the white holes themselves remain invisible to electromagnetic observations. Perhaps most intriguingly, the search for white hole signatures has led astronomers to reconsider some of the most fundamental observations in cosmology. Could the Big Bang itself represent the observational signature of a cosmic scale white hole? Could the cosmic microwave background radiation carry subtle imprints of white hole physics embedded in its temperature fluctuations and polarization patterns? These questions remain actively debated, with some researchers claiming to detect anomalous features in cosmological data that might be consistent with white hole cosmology. The observational challenge of finding white holes also highlights deeper questions about the relationship between theoretical physics and empirical science. How do we interpret the absence of observational evidence for phenomena that our best theories predict should exist? Does the failure to detect white holes tell us something fundamental about the nature of space-time, or does it simply reflect the limitations of our current observational capabilities and theoretical understanding? As we drift through these contemplations of cosmic hide-and-seek, we find ourselves appreciating how the search for white holes represents more than just an astronomical treasure hunt. It embodies the eternal dialogue between mathematical theory and empirical observation, between the possible and the actual, between the elegant predictions of our equations and the sometimes stubborn realities of the cosmos that surrounds us. In the quiet depths of the 21st century, a renaissance in theoretical physics has breathed new life into the ancient mystery of white holes, revealing connections and possibilities that earlier generations of physicists could never have imagined. As our mathematical tools have grown more sophisticated and our understanding of quantum gravity has deepened, white holes have emerged not as isolated curiosities, but as integral components of a grand unified picture of spacetime, information, and the fundamental nature of reality itself. String theory, that ambitious attempt to unify quantum mechanics with general relativity through the metaphor of vibrating multidimensional strings, has provided entirely new perspectives on white hole physics. In the string theory framework, what we perceive as particles and forces are merely different vibrational modes of fundamental strings propagating through a space-time that possesses far more dimensions than the four we directly experience. This higher dimensional perspective reveals that white holes might be understood as topological defects in the fabric of space-time itself, regions where the extra dimensions curl up in unusual configurations that produce white hole behavior in our familiar four-dimensional world. The mathematics of string theory suggests that white holes and black holes might be related through what physicists call duality transformations, mathematical operations that transform one physical description into another while preserving the essential physics. In some string theory models, a black hole in one description becomes a white hole when viewed from a different mathematical perspective, suggesting that these seemingly opposite objects might be different aspects of the same underlying reality. This duality principle implies that the universe might naturally contain both types of objects, with the apparent dominance of black holes over white holes reflecting not fundamental physics, but merely our particular observational perspective. Meanwhile, loop quantum gravity, an alternative approach to quantum gravity that attempts to understand spacetime as woven from discrete quantum threads, has revealed its own insights into white hole physics. In the loop quantum gravity framework, the infinite curvature singularities that plague classical descriptions of both black holes and white holes are resolved through quantum discreteness effects. Space and time themselves become granular at the smallest scales, preventing the formation of true mathematical singularities and potentially stabilizing white holes against the catastrophic instabilities that destroy them in classical general relativity. The loop quantum gravity description suggests that what appears as a white hole singularity in classical physics might actually be a quantum bounce, a region where the curvature of spacetime reaches a maximum quantum limit and then begins to decrease, creating the outward flow of matter and energy that characterizes white hole behaviors. This quantum bounce mechanism provides a natural formation process for white holes emerging from the collapse of previous black holes through quantum gravitational effects that become important at extremely high densities. Recent developments in holographic principles have added another layer of understanding to white hole physics. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary surface of that volume, much like a hologram encodes three-dimensional information in a two-dimensional medium. When applied to white holes, this principle implies that the matter and energy emerging from a white hole's interior might actually represent the decoding of information stored on the white hole's boundary surface, the past horizon that separates the white hole interior from the external universe. This holographic perspective transforms the white hole information paradox from a problem into a feature. Instead of creating information from nothing, white holes might serve as cosmic decoders, transforming boundary-encoded information into the familiar matter and energy configurations that populate our three-dimensional world. The information would not be created spontaneously, but would represent the holographic projection of pre-existing boundary data into the interior volume of space-time. The ADS-CFT correspondence, one of the most mathematically precise realizations of holographic principles, has provided specific tools for analyzing white hole physics in toy model universes with different geometries and symmetries than our own. These mathematical laboratories have revealed that white holes possess rich internal structure and dynamics that are invisible in classical general relativity, but become apparent when quantum effects are properly included. The correspondence suggests that white holes might play essential roles in maintaining the consistency of quantum gravity, serving as information processing mechanisms that ensure the preservation of quantum mechanical unitarity. Advances in quantum information theory have also shed new light on the nature of white hole horizons and their relationship to quantum entanglement. The Ryu-Takayanagi correspondence and its extensions suggest that the geometry of space-time itself might emerge from patterns of quantum entanglement between different regions of a more fundamental quantum system. In this emergent space-time paradigm, white hole horizons represent not fundamental features of geometry, but rather information-theoretic boundaries that arise from specific patterns of quantum correlation. This emergent perspective implies that white holes might be created and destroyed through processes that manipulate quantum entanglement rather than through classical gravitational collapse. Sufficiently complex quantum information processing systems might spontaneously generate white hole-like regions in their emergent space-time descriptions, providing natural mechanisms for white hole formation that bypass the stability and causality problems that plague classical models. The development of quantum error correction techniques in quantum computing has revealed unexpected connections to white hole physics. The mathematical structures used to protect quantum information from decoherence and noise in quantum computers turn out to be closely related to the geometric structures that describe white hole spacetime. This connection suggests that white holes might serve as natural quantum error correction systems, protecting information encoded in their boundary surfaces from corruption by environmental disturbances. Recent work on the firewall paradox, a puzzle about what happens to information falling into black holes, has also provided new insights into white hole physics. Some proposed resolutions to this paradox involve the formation of white hole regions inside black holes, where information that appeared to be destroyed by the black hole is actually processed and eventually re-emitted through white hole mechanisms. These models suggest that every black hole might contain white hole regions, creating a complex internal dynamics that processes and preserves information while maintaining the appearance of information destruction from the external perspective. As we drift through these modern theoretical developments, we find ourselves appreciating how white holes have evolved from mathematical curiosities into central players in our understanding of quantum gravity, information processing, and the fundamental structure of spacetime itself. The Renaissance in theoretical physics has revealed that these objects, regardless of whether they exist as observable entities in our universe, serve as essential theoretical tools for understanding the deepest principles that govern physical reality. There is something profoundly moving about the way white holes illuminate the deepest mysteries of existence, not just the technical puzzles of theoretical physics, but the fundamental questions of why there is something rather than nothing, why the universe possesses the elegant mathematical structure that allows for consciousness and contemplation, and why we find ourselves capable of peering into these cosmic mysteries in the first place. As we reach the gentle conclusion of our contemplative journey through the theoretical landscape of white holes, we find ourselves confronting not just exotic physics, but the very nature of cosmic creativity itself. White holes represent more than gravitational anomalies or mathematical curiosities. They embody the principle of spontaneous creation that lies at the heart of our universe's most profound mysteries. In their theoretical existence, we glimpse something essential about the creative capacity that underlies all physical reality. The poetry of white holes lies not merely in their dramatic violation of everyday causality, but in what they suggest about the relationship between mathematics and meaning in the cosmos. These objects emerge from the same equations that describe the gentle curvature of spacetime around the Earth, the orbital dance of binary stars, and the expansion of the universe itself. Yet they represent something fundamentally different, regions where the mathematical description of reality admits the possibility of pure creation, of something emerging from nothing through the sheer geometric necessity of curved spacetime. This connection between mathematical elegance and cosmic creativity speaks to deep questions about the nature of existence itself. Why do the fundamental equations of physics possess such extraordinary beauty and symmetry? Why does the mathematics that describes black holes inevitably lead to the description of white holes? Why does the universe seem to be organized according to principles that human minds can comprehend and find aesthetically compelling? Perhaps the most profound aspect of white holes is how they challenge our conventional understanding of time and causality while simultaneously revealing deeper patterns of cosmic organization. In our everyday experience, effects follow causes in orderly procession. The future emerges from the past through predictable physical processes, and creation requires creators. But white holes suggest that the universe might operate according to more fundamental principles, principles where creation and destruction are simply different aspects of the same underlying reality, where past and future are interchangeable coordinates in a larger geometric structure, where causality itself emerges from deeper symmetries that transcend our temporal experience. The philosophical implications extend even further when we consider white holes in the context of cosmic evolution and the arrow of time. Our universe began in a state of extraordinary low entropy, a highly organized configuration that has been steadily evolving toward greater disorder and complexity over the billions of years since the Big Bang. This thermodynamic arrow of time gives meaning to our concepts of past and future, birth and death, creation and decay. Yet white holes represent regions where this arrow reverses, where entropy decreases and organization emerges spontaneously from chaos. What does this tell us about the fundamental nature of time and existence? Are we living in a universe where creation and destruction occur simultaneously, where every ending enables a new beginning, where the apparent flow from order to disorder is balanced by hidden processes that generate order from chaos? White holes suggest that the universe might be far more cyclical and regenerative than our linear experience of time would lead us to believe. The connection between white holes and cosmic reproduction adds another layer of poetic significance to these theoretical objects. If baby universes can emerge from white holes, then our cosmos becomes not a singular, isolated entity, but part of an infinite family of reproducing cosmic domains. Each universe would carry forward the creative potential of its parent while developing its own unique patterns of evolution and complexity. Death and birth become cosmic partners in an eternal dance of renewal and transformation. This vision transforms our understanding of cosmic purpose and meaning. Instead of existing in a universe that is slowly dying through entropy, increase, and expansion, we might inhabit a cosmos that is constantly creating new domains of existence, new possibilities for complexity and consciousness, new theaters for the emergence of meaning and beauty. Our universe becomes not an isolated accident, but a participant in an ongoing process of cosmic creativity that extends infinitely through higher dimensional spaces we can barely imagine. The mathematical beauty of white hole solutions also speaks to something profound about the relationship between consciousness and cosmos. The fact that human minds can comprehend these exotic objects, can trace their logical implications through abstract mathematical reasoning, can find beauty and meaning in their geometric properties, suggests deep connections between the structure of consciousness and the structure of reality itself. We are not merely passive observers of cosmic processes, but active participants in the universe's ongoing self-understanding. Perhaps most beautifully, white holes remind us that the universe remains fundamentally mysterious despite centuries of scientific progress. Even our most sophisticated theories and mathematical tools can only hint at the true nature of these objects. They exist at the boundary between the known and the unknowable, between mathematical possibility and physical reality, between the elegant abstractions of theoretical physics and the complex messiness of the actual cosmos. In contemplating white holes, we find ourselves participating in humanity's most ancient and noble quest, the attempt to understand our place in the grand scheme of existence. These theoretical objects serve as mirrors that reflect our deepest questions about creation, causality, meaning, and purpose. Whether or not they exist as physical realities in our universe, they have already served their purpose by inspiring us to think more deeply about the nature of existence itself. As we drift toward the gentle conclusion of this cosmic contemplation, we find ourselves filled not with definitive answers, but with a deeper appreciation for the questions themselves. White holes have taken us on a journey through the mathematical landscape of general relativity, through the quantum realm, where particles dance with uncertainty, through the thermodynamic principles that govern the flow of time and energy, and ultimately into the philosophical depths where science meets meaning. In the end, perhaps this is the greatest gift that white holes offer us, not solutions to cosmic puzzles, but invitations to participate more fully in the ongoing cosmic conversation between mathematics and meaning, between theoretical possibility and lived reality, between the elegant abstractions of physics and the profound mystery of why anything exists at all. In their theoretical beauty and practical elusiveness, white holes embody something essential about the universe itself, a cosmos that is simultaneously comprehensible and mysterious, mathematical and magical, knowable and ineffable. And in this gentle recognition, we find ourselves not at the end of our journey, but at the beginning of an even deeper appreciation for the cosmic dance in which we are all participants. A dance where creation and destruction, beginning and ending, question and answer flow together in the eternal rhythm of existence itself.